Thanks everybody for your being here. I'm excited to talk to you about this topic today. It's something that we've been working on for about 2.5 years, building up familiarity with large language and vision models and applying those to different imagery domains. And so this is a new domain that we explored recently. The work is stemming from work that was presented at the last year's Defense and Commercial Sensing conference. And so I was so inspired by that we ran in this new direction. And so I'll be talking about that. But we're talking about geospatial and temporal data. The topic was just brought up. If you have imagery that's collected over time, you might like to observe change detection is a thing, but perhaps you want to be more specific with what you're looking for or what you'd like the algorithms to predict. So this sense-making problem, it's a big idea. The idea is perhaps you can have a general all-purpose model that can give you actionable understanding no matter what your data domain is. So maybe there's an infinite variety of different inputs that you could provide to a model at a single time. It might need to be adapted to the different data domains, but you give it imagery, you give it video, you give it sensor detections, perhaps text and reports, and the goal would be to generate finished intelligence that would describe potentially targets of interest or a situation as it develops over time. So it's a big dream. There was a talk yesterday talking about activity-based intelligence. The acronym was called ACT-INT, and it gets to this idea of, can we get to the human intent behind the actions that we're observing in geospatial imagery? As the humans, as we make an impact on the world, is there intent behind the actions that we're observing from afar? And so some of our research objectives. The satellite imagery, radar, remote sensing are all data modalities that map our world. And the temporal observations, they show these human-caused changes. But there's a capability gap right now in some of the defense and security applications that we work in. And that is that the temporal understanding is not necessarily there automatically. We don't have algorithms that have really robust temporal understanding. Maybe we can do change detection, maybe we can have little triggers and things that flag something of interest, but not necessarily a full understanding of what's going on. And so the idea is, I was hoping that this would loop, but I'll play it again. If we take a sequence of imagery that's been collected, perhaps from multiple different sensors, this is just showing one, can we figure out what events are happening during that period of time? What's likely to happen in the future on the next collect that happens? And why are these events happening? That would be the big question that we'd like to answer. And so the task is predict the state, predict actions, predict intent if we can. And so some of those labels might be, there's land clearing outside of Reno, Nevada. Maybe you can observe and you detect the beginning of a construction of a large site. There's an active construction of an industrial structure that occurs at some point. And maybe you can pre-predict that when there's a finished construction, that it's likely to be a data center based on the characteristics of what's being built during that period of time. And so this would be like an interesting sequence of generations as you uncover more imagery over a sequence. There's been lots of related research here in different domains. There's been vision transformers revolutionizing our understanding of imagery. Deep learning and convolutional neural networks were very popular. Today, vision transformers and other sorts of transformers are really the state-of-the-art methods. And so in 2022, there were smaller vision language models for embeddings, and that has developed into multimodal large language models. The tasks being image captioning. Can you generate a sequence of text that describes an image, or perhaps something that's more robust, that you can ask a variety of different questions, and that would be called visual question answering. And so those are the tasks that we're interested in, some of them. There's also this temporal aspect, which hasn't been thoroughly studied. Only very recently, in 2024, have there been any methods to approach this problem in a very robust way. I call out one of them here. Last year in November, this was published, Olmo Earth, a very large foundation model that was trained on 20 different modalities of sensors from NASA and several other space and intelligence communities, bringing all of these different data sources, covering the entire globe with all of these different modalities and other semantic layers of information, and building a foundation model out of that. And so that really interesting stuff coming from the this research community. This work was done by the Allen Institute for AI, and very specifically Joseph Redman, which was the creator of the YOLO algorithm. This is his first major work since YOLO. And there's a tie into my university at ASU, which is pretty cool. So temporal understanding is developing, and that's what we're really exploring here in this work. There's also video understanding via AI, language models, multimodal, different systems. That's a large body of work that I think is very geared in towards consumer video and YouTube type videos. It's not necessarily the right fit for overhead imagery. But some of those techniques might be still viable to this different domain, and something that we'd like to explore as well. And so some of our prior work, last year we presented a language vision model for understanding the MSTAR dataset, which is this synthetic aperture radar imagery. And so that's a limited data set, but it sort of set the foundation for some of the techniques that we're using here in this method. We also are working towards a journal paper. Right now the working title is VQATR, and we'd like to have a vehicle-focused ATR system that we can do visual question answering related to. And so another topic that I'll be presenting today is SAR-RAG for retrieval augmented generation. But there's a variety of different work that we've explored here, mostly related to synthetic aperture radar. Some of our results are on the side there. It shows that the MSTAR data set is almost a solved problem, and so we'd like to move on to harder data sets, and that's what we're exploring here. So prior key findings within that MSTAR data set and some of the work that we did previously, the key takeaways from that work are a pre-trained multimodal large language model. You can capture fine-grained detail even in SAR imagery, maybe even without a lot of fine-tuning or adaptation. If you've trained on all of the internet's scale of imagery, perhaps you're able to capture enough nuance from all of that imagery that you can apply that to even very different data domains like synthetic aperture radar or like geospatial imagery. And so when you fine-tune it, some pre-trained foundation model, you can often achieve great results immediately, perhaps better than you could do training your own model from scratch on a limited data set. And so that's an interesting takeaway, is a previous deep learning approach would be build your own model, bring your own data, label more data, keep doing it until it works. But a new methodology would be bring a big model that's been trained on the entire world's imagery and then apply it to your new domain and bring a small amount of data to better effect. And so that's called parameter efficient fine-tuning. We've done this here on synthetic aperture radar. We're doing it here on these temporal data as well. And so in these prior key findings, we saw that we could get a 40% increase or decrease in our GPU utilization based on quantization and other methods. And so if you'd like to learn more, that was the paper we produced last year. And so the technique here at the bottom, it's something that we explored in the MSTAR dataset. If you only had 5,000, 6,000 images of SAR targets, how can you get enough data to train an effective algorithm? Maybe you need to bring in supplementary data like this other 9,000. Maybe you want to teach it different questions and different answers and use all of the different metadata that you can, teaching different aspects into a language and vision understanding model. And we multiply all of those image examples by 7. You can do a generative model to augment all of the questions that you're teaching the model, and very quickly, even without data duplication, you could get to 100,000 training examples only from those 5,000. And so this is an interesting paradigm that's worth exploring, and that's something that we talk about here. So the IARPA Smart Heavy Construction Dataset has been discussed twice at this SPIE Defense and Commercial Sensing Conference. And most recently last year, this was released to the public. This was an IARPA intelligence community effort, and they produced this open source data set that's available for other people to use. And so they took Sentinel-2 EO imagery, they took Landsat, Worldview, Legion, Planet Labs imagery, all of these different image sources, and using change detection algorithms, found interesting spots on the world where there is active construction and things changing over time. And those things have been hand labeled by human analysts, and they're understood to be commercial, industrial, residential, or other sorts of zoned construction sites. And additionally, the temporal labels tell you something about what phase of construction it is at any period of time in the past observations. And so you know things that are active construction, things that are site preparation if you're clearing land for a new construction, perhaps things that relate to a finished building in a post-construction. And so there's a lot of interesting metadata here associated with this data set. It was originally intended to be used for change detection, but we're trying to use it for more of an ATR context. And so what I did is I downloaded as much of this Sentinel-2 imagery that I could, over 1 terabyte of large scene tiles, and then chipped those out with these observations. And so we have hopefully 24,000 observations, chips that we can produce from these satellite tiles. Not all of those tiles are achievable. We can't get them all from Sentinel-2, unfortunately. Some of the data holdings are incomplete, but we can still get quite a lot of data. And then after we've produced these chips and we have a particular construction site, one of many that we're monitoring over time, we can compare that chip to all of the other chips that are produced, perhaps only a few, perhaps hundreds of other chips that relate to that construction site over time. And that pairwise combinatorial comparison, that very quickly duplicates your data holdings, or your label training data, so to speak. You can draw comparisons between one image and another, and you can go quickly from 24,000 chips to 2.3 million chips, I should say labels associated with multiple chips. And so that's something, a multi-image setup here is what we're exploring. So construction site level analysis, this is just some general metadata associated with this data set that we're exploring. A lot of it's very low resolution. There's only maybe 20, 30 pixels of information that describe this small construction site at this 10-meter ground sample distance that's associated with Sentinel-2. Some of them are much larger, and so you can see the long tail on that first plot. There's also observations by site. Some of them have quite a few observations by site. many have very few observations by site, but some have quite a few observations, perhaps more than 250 observations. And so there's interesting metadata to draw here, but we would like to see sites that change over time, and those are labeled by this data set. And so our proposed method, we can leverage some of our prior work with multimodal large language models and adapt them for multi-image input. And so you could take 2 images, you could take more images if that was something that you wanted to do. You can pass all of those embeddings into the language model, and each one of those images and all of the patches that are taken from that image become word embeddings. And so each one of those small elements is treated as a word within the understanding of the language model. And so this is something that we've developed and are currently training and testing. And so our future roadmap, we would like to also incorporate the Sentinel-1 imagery, the synthetic aperture radar imagery produced by the European Space Agency and Copernicus. And so this is our next data holding that we'd like to incorporate into this body of work. We could also incorporate other sources of data, such as land use and land cover semantic maps over the world, and those might provide us additional labels, such as what was this this point of the Earth? Was it a particular zoned type of land cover at some point of time, and then during the land clearing construction process, something else was built? And we could use some of those semantic labels to inform some of these natural language captions that we're generating for this visual question answering system. And so there's other quantitative metrics that we could produce, such as what is the square area of the construction site. Each one of these quantitative measures is an interesting new metadata that we could teach into the model to help it gain a more thorough understanding and to provide more labels for the training process. And so we're working towards a next system that incorporates not only imagery over time or video sequences, but tracks of detections. And so spatial tracks, a timestamp that tracks a target through space and time, and something that would relate more to a moving target as opposed to a stationary target on the Earth. And so we have a data set associated with naval ships in simulated exercises, and that's something that we're exploring next. And so getting back to our original big goal is temporal reasoning and trying to define intent. What is the intent of what's going on in your observations? And we think we're working in that direction with this new data set, and this model seems to be giving us pretty good opportunities to infer those sort of information, as long as we can provide interesting labels for the training process. And so that is my slide deck. We're working towards more definitive results on this model, and it's something we hope to present soon. But the data here is very powerful, and it's something that we're working with. So thank you very much, and I think there's perhaps time for questions.